Hello and welcome to Morehouse's Math Menagerie. Today we're going to be talking about inference for multiple means. So let's say we know someone who's training for a triathlon and they have to bike 3 miles in this triathlon. Well, over the course of several practice laps, they record how long it takes them to bike the first, second, and third mile for their training. So here what we have is for mile 1, we have a list of 5 times. In mile 2, we have a list of 5 times. In mile 3, we have a list of 5 times. Now this cyclist wants to compare the mean times for these 3 different miles. Previously, we learned how to compare 2 means at a time. If we tried to apply that here, we would say, okay, well, let's compare mile 1 to mile 2. The mean for mile 1 and mile 3, and then the mean for mile 2 and mile 3. Now, we would have to run 3 separate tests, but we could do this if we wanted to. The problem that arises, though, is you will recall that alpha, the significance level, is also the probability of a type 1 error occurring. A type 1 error is when we reject the null, even though the null is true. Well, when you have 3 separate tests that you're running in the same situation, you end up adding those together. So overall, we would have a type 1 error of 15%. That's a little bit too high. We don't want the probability of a type 1 error to be that high. So to control for this, we actually have to run a different type of test. The test we're going to run is going to have a null hypothesis that all 3 means are equal, and an alternative hypothesis that at least one of the population's means is different. Now this test is called an ANOVA test. The ANOVA test stands for analysis of variance and is a pretty in-depth topic. We're going to kind of just skim the surface of this test today, but know that there's a lot more to analysis of variance than what we're talking about in this class. In fact, you can take entire college classes, semester-long classes that just cover analysis of variance. It gets very in-depth. Here, I've gone ahead and found the summary statistics for each of the different miles. For all 3 miles, we have a sample size of 5. Mile 1 had a mean time of 3.54 minutes. Mile 2 had a mean time of 3.328 minutes. And mile 3 had 3.514 minutes as its average. And then we have the standard deviation and the variance for each of the miles as well. When you run an ANOVA test, the test statistic is going to be an F test statistic. And that is calculated by finding the variance between samples divided by the variance within samples. And here's the actual symbolic formula for it. But let's walk through what each of these mean. If I wanted to find the variance between samples, that means I'm going to find the variance of the sample means. So I'm going to take the sample size 5 and multiply it by the variance between these sample means. I went ahead and calculated that on a calculator and got 0.010329. I would multiply that by our sample size of 5, and this is the variance between sample means. That's the numerator of our F test statistic. For the denominator, I need to find the variance within the samples. To find the variance within samples, I'm going to take the variance for each of the 3 samples, and I'm going to average them. So I add them up, divide by 3, and I get 0.02. So that's the denominator of my F test statistic. So if I put that all together here, I get the variance between samples in my numerator divided by the variance within samples in my denominator. When I divide that, I get 25.8225. I can then go to my F distribution. Remember that it is a skewed right distribution. And I can find the area to the right of 25.8225. And here I get a p-value that's very, very small when I do that. So here we would say we're going to reject the null hypothesis that the means are all the same in favor of the alternative that's saying one of them is different. And just kind of looking at the different means, we can see that mile 3 was a little bit higher, and it was high enough that we would say this is statistically significant. Okay, I want to go over to StatCrunch and do an example with you guys. Remember, we're just kind of skimming the surface of this topic, so we're not going to get real in depth. But let's read this example together. Refer to the accompanying data table, which shows the amounts of nicotine milligrams per cigarette in king-size cigarettes, 100 millimeter menthol cigarettes, and 100 millimeter non-menthol cigarettes. The king-size cigarettes are non-filtered, while the 100 millimeter menthol cigarettes and 100 millimeter non-menthol cigarettes are filtered. Use a 0.05 significance level to test the claim that the 3 categories of cigarettes yield the same mean amount of nicotine. Given that only the king-size cigarettes are not filtered, do the filters appear to make a difference? Okay, let's go and look at our table first. And I'm going to go ahead and open that up into StatCrunch first. Now, determine the null and alternative hypotheses. Here, the null is going to be that all 3 means are the same. The alternative is that at least one is different from the others. Right. Now then it says find the F test statistic. So I'm going to go back to StatCrunch here. It has the nicotine levels for the 3 separate cigarettes in columns 1, 2, and 3. So I'm going to go Stat, ANOVA, and we're just doing a one-way ANOVA today. I'm going to select here in the menu all 3 of these by either holding down Control or selecting the first, holding down Shift, and selecting the last. We actually do not need to click any of these other options. We only need to select the columns that we're running the ANOVA on. Then we can hit Compute, and we get an analysis of variance output here. For each of these, it shows the mean and standard deviation and the standard error for the different samples, king size, menthol, and non-menthol. Down below here, we have an ANOVA table that has a bunch of different information in it. For us in this class, the only thing we need to worry about is this F-stat, that's this test statistic, and the p-value. These are the 2 things that we're going to be looking at to make decisions. So for the F-stat here, it wants 4 decimal places. So 5.2164, 5.2164. Nice. And then we're going to get our p-value. They want 4 decimal places again. So 0.0121. 0.0121. All right. Now, what's our conclusion? Our significance level was 5%. Our p-value was less than our significance level, so we're going to reject the null in favor of the alternative. So only A and D are possible answers here. A says, reject the null. There is insufficient evidence to warrant rejection of the claim that the 3 categories of cigarettes yield the same amount of nicotine. That doesn't seem right. Since we are rejecting the null, there should be sufficient evidence to reject this claim. So D is probably going to be the right answer, but let's take a look at it anyways. Reject the null. There is sufficient evidence to warrant rejection of the claim that the 3 categories of cigarettes yield the same amount of nicotine. So let's select D, that sounds right. Check our answer. Now it says, do the filters appear to make a difference? We would probably say yes, since they had the largest mean, it appears that filters do make a difference. All right. I was just going to walk through one example today because all the problems look fairly similar to the one we just covered. Remember, if you're having questions while you're doing the homework, please use this Ask My Instructor button to send me an email with your questions. Thank you for joining me. Have a great day.